Hi folks, welcome to section 1.4 where we're going to talk about one-sided limits. This will be the companion to our two previous sections where we've been doing regular two-sided limits. In section 1.1 we talked a lot about how important it was to look at y values on both sides of the point we're interested in. So in this section we'll talk a little bit more about what happens if the y values on the two different sides are doing two different things. So if you remember, back in section 1.1, there were three ways that a limit might not exist. The first one was that the function might go towards different y values on the left and the right side of c. The second one was that the function might get forever smaller or larger. That was the functions that looked something like this, where my function has an asymptote and it goes up or down forever. And then the third one was that the function might oscillate wildly as x approaches c. So that would have been something like the sine of 1 over x function, where it went back and forth and back and forth and back and forth, and it made this sort of funny looking wiggle in the middle. Okay? The one we're interested in today is the ones where the functions approach different values on the left and the right side. So by the end of this section, you'll be able to calculate one-sided limits from graphs and tables and equations, and those two things will enable us to calculate limits of piecewise functions. If piecewise functions are unfamiliar to you, I want to recommend that you go take a look in our review module. There's a little bit of piecewise function review that will help you as we start encountering those. So we're going to start off with the graphs and the tables, one-sided limits, just like we did regular limits. So when we talk about one-sided limits, we're going to talk about left and right. So a left limit asks the question, what are the y values getting close to when x is moving towards c coming from the left? So let's get a picture to go with that. Here's my coordinate plane, and here's my point c. And perhaps my graph has two different things going on the left and right side of C. Perhaps on the right side of C, my graph goes off like this. But on the left side of C, it goes straight up like a line. So if I want to talk about a left limit, then I have to come from the left towards C. So that would be looking at this piece of the graph that's to the left of C, moving towards C. And I would be asking, what are those y values getting close to? Obviously, in this graph that I've just sketched, I haven't provided y values, so you can't answer the question. But the important part I want to get across here is that we're looking at the part of the graph that is to the left of C, but moving towards C. So the formal version of that, remember we had a formal definition of a limit? This is the same kind of thing, but for a left-sided limit. The only thing that comes new is the function f needs to be defined for all x near c where x is less than c, because we want to look at the x values down here below c if we're talking about a left limit. And it says if f of x becomes arbitrarily close to L, remember that arbitrarily close just meant that we could get closer and closer and closer as close as we want. For all the x's close enough to C, still where we're only looking at the x's less than C, so that they'll be to the left, then we can say that the limit as x approaches C with this little minus sign, that means the left limit as x approaches C is L. There's a corresponding sort of thing for a right limit. The only difference is that we're going to be talking about coming from the right instead of coming from the left. And then there's a definition that says the same kind of thing, except this time instead of less than C, we're going to be looking at x's that are bigger than C. If I go back for just a moment to my graph, the right side part of this limit would have been looking at this part to the right of C, but again still moving towards C. So these two definitions should look very similar. That really the only difference is that for a left limit, x is always less than c. For a right limit, x is always bigger than c. For a right limit, we use this plus on our limit point to indicate that. For a left limit, we use this little negative. Really important to notice here. If I write x approaches c with this minus on it, that says absolutely nothing about whether c was positive or negative. In the picture I was drawing, c was most definitely a positive number. But if I wanted to look at the limit as x approaches c from the left of that same kind of function, I'll keep the same kind of shape that I had just a minute ago, then I'm still going to be looking at these numbers that are positive numbers just to the left of c. All right, so that little minus, that doesn't mean anything at all about positive or negative numbers. It only means left. And similarly, if I had done a c with a plus, that would mean right. So let's see if we can read some one-sided limits off of a graph. This will be very much like what we did in section 1.1, except that we're going to read left and right limits for each point. So I'll do a little highlighting to kind of keep up with where we are. For number 1, it asks for the limit as x approaches 1 from the left. So here's 1. 1 has 2 points, 2 parts of the graph that correspond to it. I want to look at the left part of the graph. So the part of the graph that would be on the left moving towards 1 would go this way. And it looks like that part of the graph, the y values are headed towards 3. Because this point right here, its y value is over here at 3. If I want to do 1 from the right now, I'm going to look at the part of the graph that's to the right of 1, but I'm still always moving towards 1, not away from it. So as I move towards 1 on that right part of the graph, the y values are approaching -2. They're headed towards this point down here. All right, so very clearly I have y values going towards 3 on the left side of 1, but going towards -2 on the right side. They're different. Now we're going to look at -2, and we're going to do the same kind of thing. We're going to do the left and the right. So if I look at, let me erase my highlights so that we can not get too confused here. If I look at -2 from the left, that means I need to look at this piece of the graph because I'm going towards -2, but I'm on the left side of -2. And those y values are all hanging out at -3. They're just the whole way across, the y value is always -3. If I look at -2 from the right, that means I've got to get this right part but head towards -2. Well, I'm still headed to the same point, so my y values are still approaching -3. So in 1 and 2 we had different left and right side limits, but on 3 and 4 we had the same, and that's because they're headed to the same point on the left and the right. Remember that this one point up here, he has nothing to do with the limit as x approaches -2. All right, now we're going to do 0 from the left and from the right. Now, I didn't put a specific point on the graph at 0, but if you find it helpful, you're welcome to add yourself a point here at 0 so that we can see what's going on. So if I approach 0 from the left, I'm going towards 0 from the left, and it looks like my y values are headed towards 1. If I go towards 0 from the right, also looks like my y values are headed to the same spot. They're headed to about 1. I want to point out that I used this part of the graph on the right of 0 because that's the part that is moving towards 0. If I tried to use this other part over here and move towards 0, I get down here and I've reached -1, but I haven't quite gotten to 0 yet. I have to go get this piece before I can get close to 0. And then these last two problems are just a little bit of review. If I ask you for f of 1, well, at 1, it looks like we have these 2 points. We always use the solid point to identify our function value. So our f of 1 is -2 because that's the y value of this solid dot. And then f of -2, I go over to -2, and I look for its solid dot. That's up here at 1. So that's just a little bit of review. All right, let's look at a table of values to see if we can calculate a limit, very much like we did in section 1.1 again. Now there's an important feature here that a calculator might not show you, but our limit might help us see. All right, so if I want to do the first limit as x approaches 2 from the left, then that means I'm going to need to look at numbers like 1.5 and 1.9, 1.99. These are all numbers that are getting closer to 2, but they're below 2. They're smaller than 2. And then to figure out their y's, we're just going to plug those x's in to our equation that we have here and let the calculator help us. So for example, for the first y value, I would do 1.5 to the third minus 8 over 4 times 1.5 minus 2. And that tells me that I'm going to end up with something that looks like, let me see here. On the numerator, I get -4.625. And on the denominator, I get a -2. So I get a final answer of about 3, sorry, got a little dyslexic there, 2.3125. So that's my y value here. Now some of you might have gotten a little annoyed at making these tables because you have to type a bunch of things into your calculator. So I want to take just a minute and show you how you can use that Desmos app or website that I mentioned to make a table for something like this where it'll calculate the y values for you. So give me just a moment. I'm going to switch apps here. Here's my nice Desmos calculator. That's an old one. Let's clear that out. I'm going to hit the plus button, and I want to make a table. And you notice my table already has x's and y's. So I'm going to fill in the x's that I had. I had 1.5, and then I had 1.9, and then I had 1.99, and I had 1.999. Up here at the top of the table where I've got y1, I want to change that, and I want to write my function equation. So I want to write x, and then the way I make the little subscript is I do an underscore. I just have to locate the underscore on this particular keyboard. There, I just typed x1 and it's smart. x1 to the third power. And I want to subtract 8. And then I should have put some parentheses here, and I didn't do it, so I'm going to go back in and do that, so that I can divide the entire thing by 4 times x1 minus 2. All right. hey, look at there. It's already filled in all of my y values for me in this table. So I have 2.3125, just like we calculated a moment ago. I have 2.85, 2.985, and 2.998. So as I look down that table, it looks to me like those y values are getting closer to 3. So I'm going to go back to my slide, and I'm going to fill in at least approximations of these numbers so that we'll have our table. So we had about 2.85, 2.98, and 2.99. So as I look down this table, at least right here, it looks like these numbers are getting close to 3. Now, that's only one side, and we want to do both sides. So I'm going to add another page in here so that we can make our second table. So for our second table, this part is going to tell us what's going on the left side. So for the second part, we want to know what's going on the right side of 2. So I'm going to make my table again, but I'm going to use different y's. Instead of 1.5 and 1.9, I want to use numbers to the right of 2. So maybe I want to do 2.5 and 2.1 and 2.01, 2.001. And I'm going to let Desmos tell me how to fill in the y values. So here goes Desmos. And my function's still there, so now all I got to do is change my numbers. So this is going to be 2.5, 2.9, 2.99, whoops, 2.99, there we go. Now this is looking better. 2.999. Well, that one. Oop, I typed the wrong thing, y'all. Not at all what I wrote on my slide. How about 2.1, 2.01, 2.001? There we go. That looks better. That just goes to show you how easy it is to get your x values going in the wrong direction. But it's okay because we caught it and we changed it. So now if we look at our y values, got 2.81, 3.15, 3.015, and then 3.00. So let's go back to our slide. Got about the same thing. Let's see. 3.81, 3.15. 3.015, and then we had 3.001. So it looks like those y values are again going close to 3. All right. So in this case, it looks like on both sides, our y values are going close to 3. But if I graph this function, I'm not expecting there to be a point at 2 because that would give me a 0 in the denominator. So if something gives me a 0 in a denominator, that means that I should either have an asymptote or a whole. And based on these tables, this doesn't look like we have an asymptote. It doesn't look like our numbers are getting bigger or smaller forever and ever and ever. They're getting close to 3. So the important feature here that I'm referring to is there is a hole at the point 2, 3 in the graph. All right, so that wraps up this problem. We've established that the left and the right limits of this function, x to the third minus 8 over 4 times x minus 2, is 3. Both the limits are the same. And we remember that there's a hole in this graph at that point 2, 3, because the 2 would give us a 0 in the denominator. All right. So what's the connection between a one-sided limit and a two-sided limit? Well, it works like this. The regular two-sided limit is a number L if and only if both the left and right limits exist. They're not one of the does not exist ones, and they're also L. Okay? So that if and only if might be a new phrase to you. It really just means two things. It means that this statement can go either direction. If we know that the two-sided limit is L, then we can conclude that both one-sided limits are also L. On the other hand, if we know that both one-sided limits are L, then we can conclude that the regular limit is also L. All right, so we'll see that in just a moment in a graph, one that should look a little bit familiar. So this is the same graph that we looked at just a moment ago. But this time I'm asking you for regular two-sided limits instead of one-sided limits. So for the limit as x approaches 1, if we were to scroll back up, that was the first one we looked at, and the left and the right numbers were different. So just like we said back in section 1, if the left and the right numbers are different, then we would say that the two-sided limit doesn't exist. For number 2, when we looked at the point approaching -2, both the left and the right did the same, approached the same point. They both had a y value approaching -3. And since both left and right had the same limit, then we say that the limit for the regular old two-sided limit is also -3. And finally, the limit as x approaches 0, that was another one where the left and the right were the same. And so we say that one is 1. That wraps up this section. We'll have one more short video in this section about piecewise functions.